Okay, so good evening.
Hi.
Yeah. Okay, so we can start.
Okay. Uh, so this is my third lecture. So today I'm going to talk about the parabolic Green, the inner and the outer Green scheme for parabolic equations. And so in the first two lectures, in lecture one, in the first two lectures, we discussed elliptic Green for elliptic problems. So in the first lecture, we discussed the Schrodinger equation about the concentration on points. And the second lecture, we discussed the inner-outer Green for unifying equation. So this is a concentration on minimum surfaces. And so let me just go quickly. For the Schrodinger for the first lecture, we do it in two steps. And first step, we solve the problem up to finally many Lagrange multiply, and then in the second step, we make the Lagrange multiply equal 0. And for the second lecture, we construct a solution concentrating on a minimum surface. So we perturb the minimum surface in the normal direction by some h. We do an inner-outer decomposition, and with this inner problem and outer problem. And so we decompose the problem into two problems. One is inner and outer. And we solve the outer problem and plug it into the inner problem. And then we solve the inner problem, non-local linear problem by infinite dimensional reduction. And so we solve this up to a function times multiply, but the multiply is now a function. And then we adjust the beginning function h, so that the multiply function is 0. And this becomes a Jacobi operator. So this is what I discussed last time. And today we're going to do the same kind of decomposition for the parabolic problems. So in the next two lectures, I will discuss the Green method for parabolic problems. So the main idea is to extend the inner-outer Green, which I just mentioned, to the parabolic equation. Now, as in my last two lectures, the key elements in the elliptic equation is the Friedhelm alternative and modular space theory of the elliptical operators. Unfortunately for parabolic problem, we don't have Friedhelm theory for the parabolic problems. So this method, if you want to have a deep look at this method, this is contained in this paper in 2020. Yeah, it contains, and there's a full version on my website. And so the model problem I'm going to consider is a parabolic versus Limburg. So for the Limburg problem, I discussed in the first lecture, and there have been many studies on different kinds of Limburg problems. But today I'm going to discuss another type of Limburg problem. So replace the number u by minus ut. So this is called a parabolic versus Limburg problem. And for this problem, variation method does not work. Okay, I want to construct concentrating solutions. So the variation method does not work. And so the aim of my lecture are twofold. First, I want to develop a parabolic Green for constructing bubble solutions for the Limburg problem. And second, I want to develop analytical tools, not just a constructive solution, but analyze possible loss of compactness for parabolic block problems. Now, for the elliptic, there are many results on the study of loss of compactness for critical exponent problems. Okay, but for parabolic problems with critical exponent, there are very few results and there are very few analytical tools. And in this talk, I'm going to also show you the inner outer going can be a very, very efficient tool to analyze loss of compactness. Okay, loss of compactness for critical problems, for parabolic critical problems. So this is the outline of my talk. First, I give an overview of the block for Fujita. Then I will discuss the parabolic going. First, I will discuss the L2 case, which I call the L2 case, and this is dimension 5 and 6. And in my second lecture, my lecture tomorrow, I will discuss the non-L2 case, and this is dimension 3 and 4. So this is a parabolic basis limit. I take P equal to n plus 2 over n minus 2. And if I have time, I will discuss the distorted Fourier transform. So these are the three references for parabolic going. And the first one, the L2 case, you can read this paper, Carmen, Depino, Monica, Musu, in 2020. And for the non-L2 case, or including the L2 case, and this is the paper I mentioned. So in this paper, it contains both L2 and the non-L2 case. And the distorted Fourier transform is contained in this paper with Yannick and Ifuzhou for the H system. Okay, let me first give you an overview of the block for parabolic problems, and then I will introduce the parabolic going for L2 case. This is what I'm going to do today. First, in the general case, so this is the Fujita problem. So we have local well-posedness. This is well known. And so the solution blows up in finite time if this limit, the L infinity norm, as t goes to capital T, goes to infinity. And here there's a famous Fujita exponent which is n plus 2 over n. Now, the two types of block which we're going to classify, and if the block looks like ODE, so if we forget about the Laplace equation, if we just look at the ODE, you have a block in finite time, you have this type of solution. So if your block rate looks like this is called subsimilar block, looks like the OD block, this is called type 1. So in other words, you can, for type 1, the Laplace, you can just ignore the Laplace. Otherwise, it's all called type 2. So what I'm going to discuss today are all type 2 blocks. Okay, if P is subcritical, we know that all blocks are type 1, and this is the Geiger Kong and Geiger Matsu and Sasayama. They show that in the subcriticals, all blocks are type 1. So there are no type 2 blocks in the subcritical case. And Mayer and Zhang, they have a complete self-similar asymptotic behavior for the type 1 blocks. So what I'm going to discuss mostly is the critical case. This is the energy critical, and this is more difficult. And in this case, Finipas and Herrero and Velasquez, they show that in the regional symmetric case, if the regional equation, the all blobs are type 1. And Collard, Mayer, and Rafa showed that for n greater than 7, if your initial data close to one bubble in D12 norm, then there's no all blobs are type 1. And with K1, we proved that the n greater than 7, and we don't need this smallness condition. And we don't need, for any non-radial, any L infinity data, non-natural L infinity data, all blobs are type 1. So, in terms of possible solutions, all blobs are type 1. Almost we expect. However, there are type 2 blob solutions and there are sign-changing type 2 blob solutions. And the first one was constructed by Philippus and Herrera and Velasquez. This is a formal computation, and Sire and compute proof in the radial case n equals 4. And they follow this Rafa and Rodinsky approach. And with the Pino and Musso, and if so, we have a new proof using our approach, the inner outer green approach. So this is dimension 4. And the dimension 5, we construct the non-radial blobs, and with this blob rate. And in dimension 6, Harata in 2020 constructed the blob with this type of a blob rate. So I will explain why he got this type of blob rate. And in dimension 3, and you can construct blob solutions with any, with t to the minus k for any integer k. So these are the, so in the lower dimensions, you don't have type 1, type 2 blob in the critical case. Now, when p is greater than the critical case, the first result is Herrera and Velasquez supercritical case is p greater than Johnson-Langley exponent, and Collard and Collard-Mayer also proved the existence of type 2 blob in the non-radial case, and Montano and Mayer they proved that in the between the critical exponent and the Johnson-Langley exponent there are no type 2 blob, and the Pino and Monica and myself, we proved a type 2 blob in between this exponent, but with non-radial, okay, non-radial data. And recently we can also show that for p equals 3, you get blobs which on the small tube, which is similar blob on the small tube with this type of a blob rate. So there are many interesting conjectures for this problem, type 2 blob. The first conjecture is all blobs are type 1, positive blobs for type 1, and so it's open for dimension less than equal to 6. And in fact, we believe that all sign-changing solutions of blob are type 1 when n greater than 7. This is more difficult because we don't have classification. And there are also many conjectures conjectures by Collard and Rafa and Mayer. They conject that if P is not Yamabe exponent, then all blobs are type 1. But this is very difficult. This will be a very difficult conjecture. Okay, and there are also results on blob at infinity. I will not discuss here. Okay, so this is an overview of a blob, type 2 blob in the critical case and the supercritical case. And so in the remaining part, I would introduce the parabolic green method for the critical Fujita, which is the parabolic basis Nimberg. And this method is not only useful for construction solutions, it's also a very important tool for analyzing the blob solutions, as we're going to see later. So this method contains two approaches. First is the L2 case. This is the one I'm going to discuss. This is n greater than 5. And the non-L2 case is n equals 2, 3, 4. Okay. So let me now explain what is mean L2 and non-L2. So the building block for our construction is the positive Orban Tonality bubble for the critical exponent problem, and all this Orban Tonality bubble can be written in terms of m plus 1 parameters. You have translation and scaling. And you can all write the solution in terms of translation and scaling. Okay. All right. So for the building block, for the standard building block, which assume Z translation is 0 and the rotation and the scaling is 1. And we know the spectrum. So first, the principal eigenvalue is positive, and the corresponding eigenfunction is exponentially small, and this corresponding to instability for the parabolic problem. And we have n plus 1 eigenfunctions, okay, correspond to lambda equals 0, mu equals 0, and the first n they are translations, and this one is the scaling. And the rest of the eigenvalue is negative, is stable. Now, clearly, for the translations, it decays like 1 over y to the n minus 1, and is L2. So for any dimension, translation is L2. So the blob also works for translation. Now, the main problem is the scaling. The scaling is decays like 1 over r to the n minus 2, is in L2 if n greater than 5. So this is very similar to the Brezhnev problem. Yeah, in the Brezhnev problem for n greater than 4, the results is different from n equals 3. N equals 3 is a slow decay case. So here we have n greater than 5, we call the L2 case, and n equals 3 and 4, this is the non-L2 case. So today I will discuss the L2 case, and tomorrow I will do the non-L2 case. So the main result I will going to present today is the simplest one, dimension 5, exponent n plus 2 over n minus 2. And the result is for any given point, for any sufficient time capital T, you can construct an initial condition such that the solution blows up exactly at Q. Okay, and the blob rate is like 1 over T minus T. The L infinity norm is like 1 over T to the T minus T to the 3. The blob rate, the lambda, the scaling is like a T minus T squared. And furthermore, the blob is core dimension 1 stable, means except one dimension, you can find an open set, relatively open set, so that all initial data will blob like this blob rate. And in this lecture, I will just simply assume Q equals 0, and I can just simply assume X is a reduced metric, just to do the construction. So this is the theorem I'm going to present to prove today. I'm going to show you the parabolic green. So this is a very simple proof. Okay, so let's start with the Okay, so let's start with the building block, which is the Orban tangent bubble, and we know the eigenfunctions, and we know the translation, we know the scaling, and so let's start with these answers, okay, and we do a formal computation, right? So this is, we assume rigid symmetric, okay, and this is the Orban tangent bubble, and suppose our solution is the Orban tangent bubble plus some L infinity function. And we assume the L infinity function, that this is a solution to the linear Hyder equation. Okay, to the linear Hyder equation. So our initial data will be I bubble and plus I water one data. Okay, plus water one data. Now, so let's plug in those computation. So assume P equals n plus 2 over n minus 2. And S of u is Laplace u plus u to the power p minus ut. And we compute the error. So we have u plus 0 to the power p. And then Laplace u, the capital U gives you minus u to the power p. And we have u ut. Okay, so this is and we expand this, okay, this term, you get p times u to the p minus 1 plus 0 and the ut. So basically you can two terms. One term comes from the plus 0, another term comes from the ut. Now let's rescale, okay? And it's a very simple rescaling. So the error will be like lambda minus 2 u to the p minus 1 plus 0 lambda y. And this will become the scaling prime, the scaling kernel. So lambda prime times the scaling kernel. Okay? So this is very simple computation, but it tells you the idea, okay? The whole idea. So as in the initial case, if we have error like this, if we have the Bose-Lindbergh problem, we need this to be orthogonal to the scaling parameter, because we're assuming the radial symmetric, so we project everything to the scaling parameter, and you project everything in the scaling parameter, and you compute, very easy to compute. This is z to the m plus 1. So this one gives you lambda to minus 2. And this term gives you lambda to minus n over 2 lambda prime, if this is L2, if you can integrable, okay? If Zn plus 1 is L2. And then you get formally lambda prime is C times plus 0 and lambda to n minus 4 over 2. So if we look for final time block, we plug in and then from here we see that plus 0 must be negative. So in other words, your error, this part must be negative in order to have a block solution. And you also need n less than equal to 6 because there's n minus 4 here. So you need n less than equal to 6. Right? So to do this argument. So now, we also need this one to be L2. So if we want Zn plus 1 to be L2, n less than equal to 6, the only case is n equals 5, right? So for this formal reason. So for n equals 5 satisfies both property. There's L2 and this condition. So that's why n equals 5 is the easiest, okay? And this computation here, everything here is very simple, very easy computation, and we'll make this computation rigorous by the parabolic green. So the main idea is to extend the inner outer green to the parabolic equation. So what is the difference between parabolic equation and the elliptic equation? some key observation for the parabolic equation. We have 3 terms for parabolic: ut, Laplace u, and u to the power p. Okay? Now, if x is much smaller than square root t minus t, and this we call the self-similar regime, then ut is much smaller than Laplace u. So in this case, we can just drop ut. In this region, the ut would be small. So in this region, I call it elliptic region. In this region, it's like an elliptic problem. Okay? Now, when x is like a square root of t minus t, then these 2 terms take over. So this is a parabolic problem. It's a parabolic region. Now, if x is much greater than square root of t minus t, then ut is much greater than Laplace u. In this case, it's an ODE. So you see an elliptic, a parabolic, and ODE. So we have 3 regimes, okay, regions, okay. So let me introduce the parabolic inner and outer green. So look for solution for this equation, and in the main order, u will be like the Orban tangent bubble and plus order 1, and this order 1 will be added later. And lambda and psi initially they are smooth functions, okay? But these are functions we need to determine, okay? These are the functions we need to determine. So the general strategy as same as in the elliptic problem, we choose a good approximation, and we construct a general solution by linearization around u0, and so the phi will be small. And so the linearized problem for phi, similar to the elliptic problem, is phi t equals Laplace phi plus p u0 p minus 1 phi plus the error and plus nonlinear term. So this is similar to the elliptic. Okay, similar to the elliptic. The crucial part of the in-outer green now is to decompose the error into, just like the elliptic case, the infinite dimensional reduced case. We're going to decompose the error into 2 functions. So one function is eta. Eta is the cutoff function. So one function is the inner function. We use the inner variable. And this is the elliptic part. In this part, the elliptic will take over. And plus the outer problem. Okay? So this is very similar to the second lecture. We look for a solution of the initial answers plus cutoff function times phi. Phi is the inner and the psi is the outer. Okay? So phi solves the inner problem. And so we only solve this problem in x minus psi less than r. This r is a function of t. Okay? R is a function of t. And times lambda t. So we solve. So in this r times lambda t, r is actually large. Okay? But this is a function of t. And psi solves the outer problem. And eta is a suitable cutoff. So both equations form a nonlinear parabolic system. So let's fix a point in the whole space. We consider a smooth function z0 star with a z0 q initial condition is negative, and we solve this the Hyder equation with this initial condition, and this is our solution. So our solution will be initial the Orban tangent bubble plus a solution to the Hyder equation, and plus the error, okay, the phi. And the phi, we decompose the phi into the inner part and the outer part. And here for the inner part, we have to use the inner variable scaling. So lambda to the minus n minus 2 is here, is in the inner part. But outer part, we don't do any scaling. Okay, and the cutoff is in terms of the scaled variable is y over r. Okay, we plug in the new answers and plot inside, and then do some computations, and so now we have a inner outer green system. So the inner problem is like the linearize the problem, okay, linearize around the U, and the H contains many terms, contains the outer problem, the Z star, the noise, and the outer problem psi. The psi is here. Psi is inside in the inner problem, okay, and this is the error, okay, this is the error. And the outer problem, we put all the terms into outer problem. So the outer problem contains you cut the potential, and you have this A and B. What is B? A and B. So A is the cutoff function. A contains the cutoff function, and B contains lots of derivatives. Okay, derivatives come from the subsimilar variable. Okay, come from the subsimilar variable. So this is the inner to outer problem. So this is a simplified inner to outer GUI. So the inner problem is like this. So you have a linear operator, and you have the error, and the outer problem enters into inner problem by P U0 P minus 1 per psi. And the inner problem is only solved. You only solve in the inner part. You only solve the inner problem up to 2r times lambda. Now, beyond 2r times lambda, the solution may be very strange, but you don't care, because all you care is in this inner problem, in the inner region. And the outer problem, you see the outer problem is the heat equation, and you cut the Schrödinger, this part, you cut the difficult part, you put the difficult part in the inner problem. And then what you see is the cutoff function, gradient eta, gradient phi times Laplace phi, eta. So the blue color means the coupling terms. So the outer problem enter into inner problem in this way, the inner problem enter into outer problem in this way. Okay? So the question is to choose suitable radius r so that the inner outer problem decouples, so that one problem is better than the other one. Now, so what are choice of r? So first, we need r times lambda must be much smaller than square root t minus t. And because you don't want to enter to the parabolic part for the inner problem. So so the region you want to solve r times lambda must be smaller than square root t minus t. Okay, so this is the first important restriction on r. Now, if r is larger, the outer problem gains more regularity, because eta gives you r2 minus 1. Gradient eta gives you r2 minus 1. Laplace eta gives r to the minus 2. So if r is large, then you have more regularity. But then if r is large, then the inner problem gets worse, and the nonlinear problem gets worse. And we need a suitable balance. how to choose R. This is the art. This is what you need to do for each problem. Okay, and this is very important in the non-L2 case. In fact, in the non-L2 case, the choice of R is actually the most difficult part, the one of the most difficulty. Now in the L2 case, any R with this will be fine. So today I will only choose maybe R to be finite, to be independent of time, but fixed but large. Okay, just to do the proof. Okay, so let's now look at the inner problem. Now for the inner problem, we solve in the inner variable. So you have to rescale. You remember the problem has this lambda square here. So you have to put this lambda square in phi tau. So that's why you need to change a new time variable, which is tau, which is integral from 1 over lambda square. And so in the inner variable, your ansatz becomes the u, the Orban tangent bubble. And so the inner equation in terms of tau and y is a very simple linear equation, parabolic equation, with this component term. So the inner problem inner and outer problem are decoupled, and we only need to estimate from outer to inner is u to the p minus 1%. But inner to outer, okay, let's look at the inner to outer. Inner outer is given by the cutoff. It's only in the cutoff region the factor of inner and outer is filled, inner to outer. So the cutoff region is only in the y variable is y close to r. So you may find a solution which is big inside, but as long as your solution decays near the boundary, near BR, then this is good enough. This is a very important observation in tomorrow's lecture, because this is, as you are going to see, we're going to lose a lot of R's inside, but our solution near the boundary close to zero decays. And the reason that, so we have this inner to outer. The reason is the inner to outer, you only has effect in the cutoff region, okay, in the cutoff region. So this is the key, as the inner problem we found may grow large in the interior, but decays near the boundary. And for the growing to work, we need to find the inner solution which has fast spatial decay and fast time decay. So this is our model problem, okay? So we have this parabolic problem with some error h, and the h decays in time, and it decays in space. And the solution always exists. Right? This is a good thing about a parabolic, because it's a linear problem with bounded coefficients. The solution always exists. And the problem is to find a fast decay solution in both space and time. Okay? Let's recall that in general, you cannot do this. In general, because you have the solution may grow in time, because you have instability. So we have to get rid of this instability, because you have this unstable Morse index 1. The solution is Morse index 1. So we have to get rid of this mu0. Okay, so the question is, can we find a solution with fast decay in both space and time, so that phi also has decay in space, in time, and space. But we only require the Y in the self-similar regime. Because away from the self-similar regime, we don't care. Okay? So Y, when Y is greater than square root of tau, we don't care. So in the initial theory, this is achieved by Friedholm, because you write this in some variational form, right, in some space, and you write this in the identity plus compact, and then you get from fast decay solution by Friedholm theory. But for parabolic problem, we don't have Friedholm theory. Okay, so we need to find the solution. We need to construct such a solution. So first, let's get rid of the instability. So we can always find a good initial condition so that the error is orthogonal to the instability. Okay, and so by this trick, you can get rid of the instability. So we can assume that by choosing suitable initial condition, we can get rid of this instability, because you also have an instability. But if you choose your initial condition this way, you can get rid of the instability. Okay, so now this is our problem. So we choose a good initial condition, which is in this C0, C0. And so our H is orthogonal to, we assume the H is orthogonal to the n plus 1 kernels, including the translation and the scaling. And our main result is as you're expected. So if H decays in time and in space, then for sufficient R, so we need a sigma between 2 and 3. For sufficient large R, we can find a phi and C0. The C0 is your initial condition, so that your solution has decay in space and decay in time. So this is the key lemma. So this is the linear theory, parabolic linear theory for critical exponent problem. Okay, so the initial condition is not arbitrary; it's part of the solution. So you have to choose a good initial condition to get a fast decay solution, and we need a sigma between 2 and 3. And so we need to improve the first error, but this is just a technical issue. Okay, now once we have this, suppose we get an inner solution which decays like 1 over y to the sigma, then near the boundary, our y will be like r. So phi is y to the minus sigma. Gradient phi will be y to the minus 1 minus sigma. So the inner outer coupling term, okay, this one is like r minus 1. So this is r to the minus 1 minus sigma. So you get r to the minus 2 minus sigma. So this term will decay like r y to the minus 2 minus sigma. But since this is in the cutoff regime, so I can take out some part of r here and take the rest of y minus 2 minus sigma. And then for the outer problem, in the outer problem, because I already cut the U0 part, so this satisfies the maximum principle. So I can use maximum principle and to show that the solution decays, I lose a little bit decay, minus sigma over 2, but I gain some r, okay, r to the minus sigma over 2. And I will have the same time decay. So with this, now let's go back to the inner problem. and so this is the linear series for the outer problem. And if we go back to the inner problem, then the inner problem will be tau to the minus mu. The effect of outer to inner is r to the minus sigma of 2. But this one has a fast decay, which is like a minus 4. So you get minus 4 minus sigma of 2. And this is smaller than the one you start with. So, which means this term, this coupling term, is smaller. Okay, so let me repeat. We start with this type of error, and we get this solution, and then we plug into the outer problem, and we get the outer will behave like this, and then we plug into the outer problem in the inner problem. The noise from the outer problem is r to the minus sigma over 2 smaller than the one you start with. So then this is a loop that is a closed loop. So you can solve the outer problem first, the inner problem, and then plug into the outer, and the outer will go to the inner, but this new error will be smaller than the one you start with. And so by this we can get a closed loop. Okay. So now this is the whole idea of the inner outer green. So now the key part is to obtain this RPL estimate. Okay, how do we obtain this RPL estimate? So to obtain this RPL estimate, we prove this by blob argument. Okay, by blob argument. So first we can put this one inside H, so that H is orthogonal to Z0, and we can assume that this is 0. So okay, so we can assume this is 0. So we can just put a new C here, so that this function, the new H, is orthogonal to the instability part, and so our H will be orthogonal to Z0 and all the kernels. Okay, all the kernels. And this is how we get the C. Okay, the C, you just solve this C, and from this C you get the coordination 1 instability. Okay, so first from this equation here, we get phi is also orthogonal to all the kernels, including the first one, including the not kernel, including the unstable eigenvalue. Okay, and so phi, and you just multiply both sides by Zi and integrate and do some estimate. So I will not do this. Okay, so now we have a linear parabolic equation, and H is orthogonal to Z0 and Z1 and up to Zn plus 1. Phi is orthogonal to Z0 and Z1 up to Zn plus 1. Okay? And now we prove by contradiction. So let's also recall that our initial condition is phi y tau 0 equals 0. Okay? So initial condition is 0. So now we want to prove the upper estimate. So we prove by contradiction. And we assume that you have a sequence of tau k and a points yk such that this quantity is 1, right? This is how we measure phi. So which means this quantity can be achieved at some tau k, mu, and yk. And our right hand side is smaller than this. Okay, smaller than this. So So we have this this situation. We have this situation. So we can shift tau and to tau k plus tau. So first, we assume that yk is bounded. So the maximum is bounded. Now, if the maximum is bounded, then we can shift tau to tau k plus tau. Right? You shift the time. Then you take a limit. Now, this tau k goes to infinity. Right? This tau k goes to infinity. So you go backward. So when you go backward, what you're going to see is an ancient solution to the parabolic equation, because the tau k goes to infinity. So when you go backwards, you're going to see an ancient solution to the parabolic equation, and this phi is orthogonal to all kernels, okay, from 0 to 1 to 6, because our n is 5. And since I assume that yk is bounded, so I also have this decay, 1 over 1 plus y2 sigma, okay? So now we obtain an ancient solution to the linearized parabolic problem, and with all this, with decay and with the orthogonality condition. So now, that's why we need sigma greater than 2, because I need this to, I want to take a limit inside here. Okay, so this is the limit equation, and we need to say that this limit equation cannot have non-trivial solution. Okay, and first, so we claim that the phi infinity is 0. First, by parabolic regularity theory, we have a smoothness because this is an ancient solution from minus infinity to 0. And by scaling argument, we have all the decay. And so now we differentiate. So the idea is to show that ds phi infinity is 0. And then we use the elliptic non-degeneracy. And to show that d tau ds equals 0, we differentiate this equation one more time. And then we multiply this equation by phi tau, and then integrate, and we get this integration. We get this energy identity. Now let's remember this: we're doing the ancient solution. So our tau is from minus infinity to 0, and this nonlinear term, this quadratic term, is non-negative because it's orthogonal to all kernels and including the first eigenfunction. So this is bounded from below. This is greater than 0. So as a result, we get this greater than 0. But since we're doing from the ancient solution, so this will imply that this will be less than equal to 0. You just integrate, and we get a conjugation because this is, of course, is greater than 0. So we get phi tau equals 0 and L0 phi infinity equals 0. And since phi infinity is bounded, and by the non-degeneracy of L0, this is a linear combination. And so we're done. So this is the first case. Phi infinity is first case when the blob is finite. So when the blob location is finite. Now, in the second case, assume that your blob location is infinite, goes to infinity, okay? So we still have this bound. And now we do this kind of scaling, which is the parabolic version of the rescaling, okay? So you rescale your phi by this. So you want to fix the place where you have the blob, and you rescale the phi tilde. Now remember, we are inside the self-similar regime. So in other words, yk square is much smaller than tau k. So So you get tau will go to minus infinity. And this is important. So tau yk square is much smaller than tau k. So in this, when you take a limit, tau goes to minus infinity. Okay? Tau is, you have an ancient solution. So you do this scaling and you do the classical convergence, and what you get is an ancient solution to the Hyder equation, okay, but with singularity. And the singularity, we can assume the singularity at 0. And we have this, the singularity is z to the minus sigma all the way to infinity, okay? So this is the ancient solution to the Hyder equation. Now, if we don't have this phi tau, then this is very easy to prove, right? This is removable singularity for elliptic equation. So now we need a removable singularity for the ancient solution for the Hyder equation, okay? And this is, again, this is from the maximum principle. So, so prove that the phi tilde is 0. And since we're doing the ancient solution, we can construct a barrier, and we add this fundamental solution so that to control the 0. Near 0, we have a control. And this is the barrier. It's y squared plus c times tau. And you do a direct computation, you found that this is the barrier, and you can take a c positive. And since my tau is going from minus infinity, right, minus to 0, so I go from minus m to 0, okay, and take m large enough, then this one will be large enough, very large, and I will get phi tilde is less equal to this from rho and tau plus m. And since my m is, since this is ancient solution, I can all the way go to minus infinity. So letting m go to infinity, I will get that this is 0. So this is a simple maximum principle argument with isolated singularity, the ancient solution for the Hyder equation. So let me summarize. We have now the proof, the RPL estimate for this linearizer problem. And we prove this RPL estimate by bluff argument, okay? By bluff argument, and we have two limits. The one limit is the linearizer, the ancient solution for the linearizer problem, parabolic linearizer problem, and the second one is I isolated the singularity, the singular ancient solution for the Hyder equation with isolated singularity. And with this, in both cases, we use the maximum principle and energy method. We get the proof. Okay. So now we have the linear theory. Now we're ready to carry out the proof. Okay, the proof of the construction. So let's recall we have in dimension 5, our P is m plus 2 over m minus 2. So we want to find a tube of functions lambda psi and phi and psi. So lambda psi will be, we need to find phi and psi, this is inner part and the outer part. We also need to find lambda and psi. So this is all the functions we need to find out. Okay, these are the ODEs we need to find, and these are the PDEs we need to find. Okay, so we form this problem as a fixed point theorem in a small region in a suitable Bangalore space. So first set up the inner problem. So to set up the inner problem, we solve. We put this in a sort of Lagrange multiplier, just like the lecture 1 and lecture 2. So this is the Lagrange multiplier. So we project H, to Zj. So this is the Lagrange multiplier. And we solve this linear problem with the Lagrange multiplier and with some initial condition we need to solve. And this is the effect of outer to inner. And so we found a solution to the inner problem because we found the linearized problem, we found a solution to the linearized problem. We take an inverse of that one, and this becomes a nonlinear operator. And so this, and to solve the inner problem is solved after the Lagrange multiplier. So we also need the Lagrange multiplier equals 0. And the outer problem can be written in terms of the inner problem. And this is a system, a coupled system, and we can use the Richelder fixed point theorem to solve the problem. So now the main problem is to solve the Lagrange multiplier, the Cj equals 0. So what is Cj? It turns out, what is the error here? This is the error. The main term in the error is lambda dot and the Kz dot. So you just like in the elliptic equation, you multiply both by Zj, and you found the equation for lambda. And this is exactly the equation that we derived at the beginning. And here, this is a rigorous proof, right? This is exact. The ODE for lambda, this is precise equation for ODE for lambda, and we get also ODE for the location, ODE for the location, and for n equals 5, we get precisely lambda equals t minus t squared, and this gives the proof. So so this is the whole fixed point argument, and we put this in a Richelder fixed point argument, and by compactors, and we get the solution. So this is an n equals 5 case. Now let me give some remarks on n equals 6. N equals 6 as in our previous computation, if we have a solution like this, process 0 is a solution to the linear heat equation, then we put it into the error here, and we compute the formula, and we get in dimension 6, you get a number prime as process 0 lambda. And then you don't get a blob in this way. Okay? If your phi 0 is a solution to the linear heat equation, and what you get is number prime equals is like a lambda, and you get the exponential growth or decay. So you don't get a finite time blob. So in order to get a finite time blob, you have to adjustify your outer problem. So the outer problem, what you need to do, the outer problem will be no longer bounded. The outer problem will be a type 1 singularity for the critical exponent. So for the outer problem, you use the self-similar solution for the critical exponent. And so by matching the inner and the outer, and you can prove the existence of the blob solution in dimension 6 with this weight. So the difference between dimension 5 and 6 is how you choose your processor. In dimension 5, we just simply choose the linear heat equation, a solution to the linear heat equation. Now in dimension 6, you have to choose a type 1 blob. So this is a type 1 blob. On the top of a type 1 blob, you have a type 2 blob in dimension 6. And and this has been proved in this Harata's paper. Okay, but once you realize this, you can do the same green. It's the same type of green we did. So and because this is L2 case, so everything is very similar. Okay, so this is the dimension 5 case, the L2 case. Now in the remaining time, I have a few minutes. I want to discuss another type of construction, which is the bubble tower construction. So in this paper with Manuel de Pina and Monica Musso, we show that for n greater than 7, and you can have construct solutions with sign-changing bubble tower. Okay, so one bubble, infantile blob. This will be infantile blob, but these are the sign-changing bubble tower. Okay, and the bubble rate, each of the bubble, they satisfy this type of estimate. And recently there's a very nice result by Mel and Kim. They in CPAM, they showed the convex. They show that if you have a bubble tower in the rigid symmetric case, and the bubble tower must be like this rate. So they proved that we constructed the sign changing bubble tower, but Mel and Kim they classified the bubble tower blob rate, and this is the only bubble tower blob rate we can have. So one can also find Asian solution for the basis, the parabolic basis problem. Now this Asian solution is quite different. So in the Asian solution are very important in Ricci for mean curvature flow, Ricci for Yamabe flow, and the only known result in the Asian solution classifications is by Mayer and Zhang, and they show that if P is subcritical, if you have Asian solution which can be controlled by the self-similar blob rate, it must be the constant blob rate. And Cornot, Mayer, and Rafa, they also construct Asian solution. So what we prove with the Sen and Zhang, we prove that when n greater than 7, again when n greater than 7, we can find the rigid symmetric positive Asian solution. So now the Asian solution are not sign changing. So in the forward solution is sign changing, but in the Asian solution we get positive Asian solutions, and the blob rate is like this. It's when t goes to minus t, the blob is t to the minus this power. Okay, and so this is a bubble tower, Asian bubble tower at infinity. Okay, so let me now, in the remaining 5 minutes, let me now show you the proof of this, and the idea is, so once you have the linear theory, of course, then the rest is you have to design a good topology to do the fixed point argument. So we assume that we have this blob rate, okay, mu k and mu k minus 1 and mu 1, and we, for the first bubble, we take a order 1 first bubble, and the rest of the bubbles will be large bubbles, and this is our first answers. Okay, we put first answers, and we put this first answer plus phi 0, and so now because of the bubble tower, so the interaction between one bubble to the next bubble is in some eigenless region. So we have to take care of the eigenless region. So we have this is the linearized operator, and so this is the bubble tower, and this is this is the first one, okay, is order 1, and then the rest, this height gets larger and larger. And so how do you get this bluff rate? So you get a bluff rate is by you compute the energy, you compute the error, and then you compute the interaction, and you do the infinite time, you do the inner outer going, and then you found the equation for the CJ, and equation for CJ, you're going to get this system of ODEs, and this system ODEs give you exactly this bluff rate. Okay, so so this is the whole procedure, but the rest of it is very complicated because we are doing this bubble tower. So what I'm going to I will show you that this procedure also works for the bubble tower, not just for one bubble, but for the bubble tower. And okay, so this is the topology, and this is the linear theory, right? This is the linear theory, and this is the outer problem because we're doing the Asian solution. So we use the Duhamel's formula to find the outer problem, and this is the topology for the outer problem and the inner problem, and so lot of computations, but in the end you're going to get a system of ODEs which you can solve, and you found the solution. So what I discussed today is the L2 case for the parabolic problem, and I use the dimension 5 as the example, and the main problem. So we do the inner outer going, and we found we found out the outer to inner and the inner to outer, and we just need to find a solution for the inner problem with fast decay in time, fast decay in space, and to do this, to get this, we use the bluff argument. So so the bluff argument will be in the boundary region. You get an Asian solution for the linearized parabolic problem, and in the infinity you get an Asian solution with isolated singularity. And with this, we get the upper estimates, and then the rest we just you formulate this in the outer going, and with the Lagrange multiplier, and you found the solution with the Banachar fixed point. Now, all this, okay, everything depends on linear problem, and unfortunately in dimension 4 this breaks down, and in dimension 3, dimension 2, dimension 3, dimension 4, all this break down, and in this case we have to be very careful. So we cannot do bluff argument because there's no this does not make sense now. This type of orthogonal condition doesn't make sense because your ZJ is not L2. So now in the dimension 3 and 4 we have to do a different argument. And dimension 2 in the harmonic map we also do a different argument. And this is what we're going to do tomorrow. We're going to study dimension 4 or dimension 3 and dimension 2. And we're going to see a completely new argument for the linear theory. Okay, and that's for today. Thank you.
Any questions?
Yes. So I have a question. So it's not a proper question, more of a philosophical question. So you have this construction of bubble tower solution, sign changing bubble tower solution. So
Yeah.
In dimension bigger than equal to 7. So do you think in certain dimension maybe bigger than equal to 7 again, or low dimension you can construct something like the crown solution, which you introduced?
Yeah, this is a good question. I think if we use the Orban-Tanani bubble, then the only bubble tower you don't I think in the Mayer and Kim, they show that for dimension 6 you don't have bubble tower. So, but the bubble tower with if you use the Orban-Tanani bubble. Yeah, I have not done the using the crown solution. That's a very interesting question. Because in dimension 6, the crown solution can be L2, right? So you can maybe, yeah, this is a good question, but I have not, yeah. So the crown solution becomes the L2 case in dimension 3.
Thank you. Thank you.
Any other question? Okay, any questions online? Okay, looks like there are no questions. And okay, so let's thank the speaker once. Okay, thank you and see you tomorrow.
Yeah, thank you. See you tomorrow. Thank you for staying so late. Thank you.